So now we have already seen how we can simultaneously diagonalize two matrices. Now let us see an example of it. So here we have matrix A 0 2 2 0 and matrix B 3 2 2 3. So you can easily notice then that AB is same as BA as shown here. So now we want to diagonalize these matrices simultaneously. Notice that matrix A is a peculiar matrix in the sense all the diagonal elements are zeros. So it is as if we are trying to achieve exactly opposite of what already A is. So let us see how it is to be done. So as you remember the process, first we need to find out the eigenvalues of both these matrices. Then we will try to find the common eigenvectors and then we'll use those eigenvectors to construct the matrix C, which will be required for diagonalization of these matrices. So let us first find the eigenvalues of A. Like this, we get the eigenvalue as 2 and minus 2. Then similarly, the eigenvalue of B is 1 and 5. So 2 and minus 2 are the eigenvalues of A and 1 and 5 are the eigenvalues of B. So now suppose U and V are the eigenvectors of A corresponding to 2 and minus 2. Then the equation will be AU equal to 2U. So say lambda 1 and lambda 2, if they are the eigenvalues of A, then lambda 1 is 2 and lambda 2 is minus 2. Similarly, if beta 1 and beta 2 are eigenvalues of B, then beta 1 is 1 and beta 2 is 5. Something like this. But we should remember the order in which we consider the eigenvalues. Or just to avoid the confusion, you can by default consider them in increasing order. Doesn't matter. So, but you do need to remember the order. So here I am considering the eigenvalue 2 first. So the equation will be AU equal to 2U and AV equal to minus 2 times V. So let us now try to solve them and see what do we get. So when we solve AU equal to 2U, we get the equation like this. So we get twice U1. Here also we got 0 times twice U2 here, and here we got twice U1 and here we have twice U1 equal to twice U2, means simply U2 equal to U1. So actually, even though it looks like we have two equations, we don't have, we have only one equation, that is U1 equal to U2. So in short, if 2 is the eigenvalue, then any vector where the first element is same as the second element, that will be an eigenvector of A corresponding to 2. So by eigenspace, what do we mean? Here in this context, the eigenspace of A with respect to the eigenvalue 2 will be collection of all paired vectors U1, U2, where U1 is equal to U2. So now similarly consider the second eigenvalue AV equal to, so the second eigenvalue is minus 2. So AV equal to minus 2V gives us 2 times V2 here, and here we have 2 times V1, and here we have minus 2 V1 equal to minus 2 V2. So when you simplify, you get V1 plus V2 equal to 0. So again see, notice that here I have infinitely many choices of U1, U2 such that U1 is equal to U2. Similarly, here I have infinitely many choices of V1 and V2 such that V1 plus V2 equal to 0. So entire line V1 equal to minus V2 is going to fulfill this equation. So I don't have one eigenvector corresponding to one eigenvalue. I have a bunch of eigenvectors, a huge bunch. You can say infinitely many eigenvectors corresponding to one eigenvalue. And that's why we can say that if I am being given one eigenvector, I can always try to find another eigenvector corresponding to another eigenvalue which is orthogonal to the one, to the first one. So now, okay, now let us see, try to understand this more. So these are the equations which need to be fulfilled if we want to construct the eigenvectors corresponding to 2 and minus 2. Now similarly, let us see what happens to the matrix B. So now for the matrix B, we have By equal to Y. So the first eigenvalue was 1 and the second eigenvalue was 5. So corresponding to the 1, suppose y is the eigenvector corresponding to the eigenvalue 1 and z is the eigenvector corresponding to the eigenvalue 5. So we will have equation by equal to y and bz equal to 5z. So when we solve it, what do we get is, see this. So I have 3y1 plus 2y2 equal to y1 and 2y1 plus 3y2 equal to y2. So when we simplify this, what do we get is y1 plus y2 equal to 0. Similarly here when we simplify, we get for the 5 value, we get 3z1 plus 2z2 equal to 5z1 and 2z1 plus 3z2 equal to 5z2. So upon simplification, this becomes z1 minus z2 equal to 0. So again we have almost same set of equations. See, here the equation was u1 minus u2 equal to 0 and v1 plus v2 equal to 0, whereas here the equation is y1 plus y2 equal to 0 and z1 minus z2 equal to 0. So now the problem comes down to the problem of identifying the eigenvectors. So now because infinitely many possibilities are there, I thought of considering the simplest answer. So I took u1 equal to 1. So if I plug in u1 equal to 1, I get u2 is also equal to 1. So 1, 1 became my eigenvector corresponding to the value 2. Similarly, I took v1 equal to 1. Then I got v2 equal to minus 1. So I got the eigenvectors. The first eigenvector was 1, 1. The second eigenvector was 1 minus 1. Now I want to see whether these are eigenvectors of matrix B also. So if I take 1, 1 here, for example here z1, z2. Then if I put z1 equal to 1, I get z2 also equal to 1. So 1, 1 is common eigenvector of A and B. The eigenvalue for 1, 1 in A is 2, whereas here it is 5. Similarly, 1 minus 1, if I put, see for example here, if I put v1 equal to 1, then v2 is equal to minus 1. So 1 minus 1 was the second eigenvector of A. So if I see the condition here, then if I put y1 equal to 1, then y2 I get as minus 1. So 1 minus 1 is the second eigenvector of B also. So I got common eigenvectors as 1, 1 and 1 minus 1. But they are not normalized eigenvectors. In the sense their norm is not 1. So to normalize them, I'll have to divide each element by the norm. So the norm here is root 2. So I'll divide, for example, the norm for the vector eigenvector 1, 1, the norm will be 1 plus 1, so 2, and the root of that will be root 2. So root 2 will be the norm. So I am dividing each element by root 2. So I will get the vector as 1 by root 2, 1 by root 2. Similarly, the other vector, eigenvector will be 1 by root 2 upon 1 minus 1 by root 2. So thus I got the common eigenvectors after normalization as 1 by root 2 minus 1 by root 2 and 1 by root 2, 1 by root 2. So notice that these both are eigenvectors of A and B both. And so we can put them as columns of the matrix C. Moreover, these P1 and P2, they are orthonormal to each other. In the sense, P1 prime P2 is equal to 0. So, and P1 prime P1 is 1, P2 prime P2 is also 1. So, I got the matrix C as P1 as the first column and P2 as the second column. So, let us see if this matrix is actually working or not. So, C prime AC, if you calculate, you get the diagonal matrix like this, minus 2, 0, 0, minus 2. And notice that these are the eigenvalues of matrix A. Notice that 1 by root 2 minus 1 by root 2 was eigenvector of A corresponding to the value minus 2. And so we have got minus 2 here. Similarly, 1 by root 2, 1 by root 2 was the eigenvector of A corresponding to the value 2. And so we got 2 here. So you get the eigenvalues here in the diagonal of the C prime AC. The diagonal elements are nothing but the eigenvalues of the matrix. So now C prime BC. Let us see what C prime BC is. So C prime BC is again 1005. So which is again the eigenvalue of matrix B.